Welcome to the Explainer. So today we are tackling the absolute building blocks of motion for your GCSE forces unit. Look, if you've ever felt totally tangled up in all those arrows, newtons, and endless formulas, don't worry. We're going to break the whole thing down visually, step by step, so it finally clicks. Let's just dive right in, shall we? Okay, here's our rapid-fire revision checklist. 1. Scalars and vectors. 2. Gravity, mass, and weight. 3. Resultant forces. 4. Resolving forces. And finally, number 5, work done.
Right, let's hit section 1. Scalars and vectors, the language of physics.
So before we can even start calculating how things move, we've got to get our vocabulary straight. There's a pretty stark contrast between these two fundamental ideas. On the left, we've got scalars. These guys have magnitude only, basically just a size, like mass or speed. But over on the right, vectors. Vectors have magnitude and direction. Think weight, velocity, displacement, force. Just adding that specific direction literally changes the entire physical meaning of the number. And because direction matters so much here, we visualize vectors using arrows. It's actually a brilliant system. The length of the arrow, that's your magnitude, the size of the force, and the arrowhead points exactly where it's acting. Grasping this is the absolute foundation for solving pretty much every single force problem you're going to see on your exam. Moving on to section 2, gravity, mass and weight, the pull of the Earth. Now, this is probably the most common exam pitfall out there. Mass and weight are absolutely not the same thing. Do not mix these up. Mass is a scalar. It's simply the amount of matter an object is made of, measured in kilograms. And it doesn't change whether you're sitting here on Earth or floating in deep space. Weight, on the other hand, is a vector. It's the actual force of gravity pulling down on that mass, and it's measured in newtons. So how do we actually connect the two? Well, you need to burn this number into your memory. 9.8 newtons per kilogram. That is Earth's gravitational field strength. To figure out an object's weight, you just take its mass in kilograms and multiply it by 9.8. They're directly proportional, sure, but you absolutely need this specific number to translate regular matter into a gravitational force. Okay, section 3, understanding resultant forces. Think of this as the ultimate tug of war.
All right, let's dive into what happens when multiple forces push and pull on something all at the exact same time. Whether it's contact forces on a car, say 50 newtons pushing right and 30 newtons pushing left, or a swimmer fighting against water resistance, it can look super chaotic. But here's the trick. We can simplify all of these competing arrows into one single overall arrow. We call that the resultant force. So for that car, 50 minus 30 leaves us with a resultant force of exactly 20 newtons pushing right. That one single force tells us everything we need to know about how that object is going to move.
But wait, what if the forces perfectly balance out? Say we've got 30 newtons pulling down from gravity and exactly 30 newtons pushing right back up from the surface. Notice how these completely cancel each other out to zero? When the resultant force is zero, we say the forces are in equilibrium. And remember, a zero resultant force just means the object is either completely stationary or it's moving at a steady, constant speed in a straight line. Let's shift gears to section 4, resolving forces and vectors, drawing the solution. This is a hugely practical exam skill. We can actually bypass a lot of confusing math just by drawing the solution using the tip-to-tail method. It's 4 easy steps. Step 1, choose a realistic scale, like, say, 1 centimeter equals 10 newtons. Step 2, draw your first vector arrow and then start your second arrow exactly where the first one ends, literally tip-to-tail. Step 3, draw a brand new line straight from your very first starting point all the way to your final endpoint. And step 4, simply measure that new line's length to get your magnitude and grab a protractor to find the angle. Boom, done. Let's actually see this in practice, because it builds together perfectly. Imagine a boat being pulled by two 100-newton forces at perfect right angles. To find our resultant force, we just construct our tip-to-tail triangle. That diagonal line, the one drawn from the very start directly to the finish, is our resultant force. If you measure that line using the scale you picked, it reveals a force of about 141 newtons acting diagonally. No crazy equations, you've solved it entirely just by drawing. And finally, section 5, work done and energy, the cost of movement. Now, what's really fascinating here is connecting all those force arrows to the actual energy it takes to move stuff. We have a very precise definition to remember. Work is the transfer of energy.
In physics, work definitely doesn't mean doing your homework. It means a resulting force has successfully moved an object through a distance. Whenever that happens, energy is being transferred from one store to another. And listen closely, if there's no distance moved, there is zero work done. Literally none, no matter how hard you're pushing.
To make this super easy, here's a visual cheat code for your exam: the formula triangle. Energy transferred, or work done, sits right at the top, and that equals force multiplied by distance at the bottom. E equals F times D. You just cover up whatever letter you're trying to find, and the triangle literally tells you whether to multiply or divide. It is a total lifesaver. So the absolute most crucial takeaway from this equation is the unit conversion. 1 joule of energy is transferred when a force of 1 newton moves an object by 1 meter. Therefore, 1 joule is exactly the same as 1 newton meter. Oh, and here's a really important fact. Whenever you do work against frictional forces, energy gets wasted, and it almost always causes a temperature rise in the object. To wrap up this explainer, I want to leave you with a thought-provoking real-world scenario to really test out your new physics intuition. Think about a massive, heavy car just flying down the highway. It has a huge amount of kinetic energy, right? Well, if it suddenly slams on its brakes, doing a massive amount of work against friction to come to a screeching halt, where exactly does all that energy go? I mean, just imagine the intense heat on those brake pads. Keep that in the back of your mind as you look at the physical world around you. Thanks for hanging out with me for this explainer, and good luck crushing those exams.